Welcome to the deep dive. Ever really stop and think about what's actually happening, deep inside your computer when you click something? At the most basic level, our source explains it really well. A computer just reads, modifies, and writes sequences of numbers.
That's it, essentially. And to really get a handle on how that device works, we're diving into Inside the Machine, an illustrated introduction to microprocessors and computer architecture. The author, John Stokes, he's got this great background, co-founder of Ars Technica, senior CPU editor there, so he knows the practical side.
Right, the real world stuff.
Exactly. But he also has the academic chops, degrees from Harvard. His book really tries to show us the fascinating stuff beyond just, numbers.
And that's what this deep dive is all about for you. If you're prepping for a tech chat, or maybe just want that solid foundation, or maybe you're just curious about your digital life.
Yeah.
We're aiming to give you the shortcut. We're pulling out the really crucial ideas from the source, kind of distilling it down, without getting bogged down in too much detail, the core stuff you need.
Yeah, and today we're going to unpack some really key concepts. We'll start with the absolute foundation, the fetch-execute cycle. Then look at how processors get so fast, pipelining superscalar execution, those clever tricks.
Yeah.
We'll also dig into instruction set architectures, ISAs are super important, and trace how processors evolved, looking at examples like, Intel and the PowerPC story.
All right, let's jump in. This fundamental read, modify, write cycle sounds technical maybe, but it's like the absolute heartbeat of everything a computer does, isn't it?
It really is. Think about that file clerk analogy again. The computer reads your input, say, a mouse click. Then it uses a set of rules. That's the program to modify things. That's the processing happening under the hood. And finally, it writes the result, what you see on screen. And it's doing all this while remembering the history of what it did before. It's this constant loop. Read, modify, write. Everything inside is built for that.
Which leads us straight to this, revolutionary idea. The stored program concept. We totally take it for granted now, but it changed everything.
Oh, absolutely. Think about it. Before stored programs, you had to manually enter every single step for every calculation. Imagine that.
Wow. Just tedious.
Totally. The idea that you could store instructions inside the computer's memory and then reuse them, that's what made modern computing possible. You needed three things, really. Storage for numbers and instructions, something to do the math, the ALU, arithmetic logic unit, and the ability to store and rerun those instructions. Figure 1 to 3 in the book shows a simple version. ALU, storage. Pretty basic.
Okay, so the ALU is doing the math, but it needs the numbers really fast, right? That's where registers come in.
Precisely. Registers are like these tiny, super fast storage spots right next to the ALU. Because they're so close, grabbing data is almost instant. Huge speed boost.
But there aren't many of them.
Right. They're built right onto the chip, so space is limited. Early x86 chips, for example, only had 8 general-purpose ones. They're grouped together in what's called a register file. Think of it as a small, elite storage area just for the ALU's immediate needs.
So numbers are in the registers, ALU's ready. How do we tell it what calculation to do? Instructions.machine code. That's the next piece.
Exactly. Let's take a simple example. Adding numbers from register A and register B, putting the result in register C. In a simple hypothetical computer, the DLW1, the instruction might look like add A, B, C.
Okay, like a command.
But the computer doesn't get add or A. It needs binary, machine code. So add gets its own binary code and opcode, maybe 000, like in table 2.1. And each register, A, B, C, D, they get codes too. 000 for A is 01 for B, 10 for C. Table 2.2 shows this.
Wow.
You string these binary codes together, the opcode, the register codes in a specific format, maybe 16 bits. That's your machine language instruction, just a number the processor understands. And that's why people say code, whether it's binary, assembly, or a high-level language. It all boils down to this machine code eventually.
Okay, that sounds incredibly detailed at the hardware level. How does a programmer actually work with that? That's the programming model, I guess.
That's exactly it. The programming model is the programmer's view, their interface with the chip. It hides all the super complex hardware stuff. Figure 2.7 shows a good example for an 8-register machine. It shows the ALU, registers, the input-output stuff, and crucially, parts of the control unit, the program counter, or PC, which tracks the next instruction's address.
Like a bookmark.
Kind of, yeah. Then the instruction register holds the current instruction being worked on, and the processor status word, PSW, stores info about recent results, like did the last math operation result in 0? Stuff like that.
So the PC points to the next instruction, normally just the next one in sequence. But programs aren't always linear, are they? Loops, decisions. That's where branch instructions come in.
Exactly right. Branches let you jump around. Non-sequential execution. Think, if this, then go there. Conditional jumps use that PSW we just mentioned. Say you subtract two numbers. If the result is 0, maybe a 0 flag gets set in the PSW. A jumps instruction program 22 has an example checks that flag. If its set result was 0, the PC gets loaded with a new address, the branch target, and boom, execution jumps.
And if not?
If not, the PC just increments like normal, goes to the very next instruction. This branching is fundamental. Without it, programs would be incredibly basic. So our simple fetch, decode, execute cycle gets a tweak. Fetch, decode, execute, and execute might mean changing the PC to jump somewhere else.
That makes sense. But how does it all even start when you turn the computer on?
Great question. It can't just start anywhere, right? When you power up, the processor is hardwired to look at a very specific memory address for its first instruction. That instruction is the beginning of the BIOS basic input-output system. It's stored in ROM, read-only memory, on the motherboard. The BIOS does some hardware checks. Then its main job is to find and jump to the bootloader program. The bootloader then finds your operating system on the hard drive or SSD and loads that. Then the OS takes over, running everything else.
Okay, got the basics. Fetch, decode, execute, branching. But modern processors are so much faster. How do they do it? Pipelining is one big reason, right?
Absolutely. Pipelining is key. The book's analogy of an SUV factory is perfect here.
Oh, yeah.
Instead of one team building a whole SUV, you have specialized teams. Chassis team, engine team, paint team. Each SUV moves down the line.
Right, an assembly line. Figure 3.5 shows that.
Exactly. A pipeline processor does the same with instructions. It breaks instruction execution into stages. Fetch, decode, execute, write back maybe? The crucial thing is the processor works on different instructions in different stages simultaneously.
Multitasking at the hardware level.
Pretty much. While one instruction is executing, the next one is decoding, the one after that is fetching. If each stage takes one clock cycle, once that pipeline is full, you essentially complete one instruction every clock cycle. Huge improvement over doing one whole instruction before starting the next, like SUVs rolling off the line much faster.
That makes total sense.
Yeah.
Overlapping the work.
Would say.
But then things got even faster with superscalar computing.
Yeah.
How does that build on pipelining?
Superscalar takes parallel processing even further. Pipelining overlaps stages of different instructions. Superscalar processors can actually complete more than one instruction in the same clock cycle by having multiple execution units working in parallel, like having several ALUs or multiple assembly lines in our factory analogy.
Okay.
Figure 4.3 shows pipelining and superscalar combined. The key metric becomes IPC instructions per clock cycle. Superscalar aims to boost IPC by adding more hardware, letting multiple instructions finish simultaneously.
So it's not just one ALU doing everything anymore. Modern chips have different kinds of execution units, specialized for different jobs.
Exactly. You don't just get multiple identical ALUs, you get specialized units. We know the ALU for basic integer math and logic, but then you have floating point units, FPUs for decimals and scientific stuff. Load store units handle moving data between the processor and memory. Branch units are optimized for those jump instructions.
Right.
Figure 4.5, the diagram of the Intel Pentium shows this. It had two integer units, one simple, one complex, and a separate FPU. And just to clarify, ALU is the general term, but we often use IU for integer unit and FPU for floating point unit to be more specific.
Okay, this hardware is getting complex. Multiple units, pipelines.
Oh.
How do programmers write software that runs on all this different hardware? That sounds like where the ISA, the instruction set architecture, comes in.
Yes, the ISA is absolutely crucial. It's the bridge. It's the programmer's abstract view of the processor. It defines the programming model, the registers, how memory looks, and the instruction set, the list of commands the programmer can use.
So it hides the internal complexity.
Exactly. Remember our simple DLW1. Its IS reflected its simple hardware. Now imagine a DLW2, maybe it adds a second ALU, making it superscalar inside, but the ISA could stay the same. The programmer wouldn't necessarily see the internal change.
Ah, interesting.
The ISA defines what the processor does from the software side. The microarchitecture is how it does it internally. This separation, shown nicely in Figure 4.7, is key. It means software written for one IS can run on different processors implementing that ISA, even if they're built differently inside. huge for software portability.
And these ISAs evolved. They add new features, like for floating point math or multimedia stuff.
Absolutely. To add floating point, engineers had to extend the ISA, add an FPU, add new floating point registers, add new instructions for programmers to use. Intel did this with by87 extensions to by86, and later with MMX and SSE for vector processing, doing the same operation on multiple pieces of data at once.
Like for graphics or video.
Exactly. PowerPC added AltiVec or VMX for similar vector stuff. These extensions make specialized tasks much faster. And it's worth remembering the difference between CISC and RSC ISAs.
Complex versus reduced instruction set computing.
Right. By 86 is CISC lots of complex variable length instructions. PowerPC, IMIPS, ARM are generally RISC, simpler, fixed-length instructions. RISC often relies more on smart compilers to optimize the code.
Okay, going back to pipelining and superscalar, you mentioned hazards, things that mess up that smooth parallel flow.
Yeah, hazards are basically roadblocks. They cause stalls or inefficiencies. Three main types. Data hazards. Instruction B needs the result from instruction A, but A isn't finished yet.
Okay, dependency.
Structural hazards, not enough hardware. Maybe two instructions need the same resource, like trying to write to the same register file port at the exact same time. Program 4.3 hints at this. Control hazards, these come from branches. The processor fetches ahead, but if it takes a branch, it might have fetched the wrong instructions. It has to figure out where to go next. Architects have lots of tricks to minimize these stalls.
And one of those tricks for superscalar chips is register renaming. Sounds clever. How does that work?
It is pretty clever. It tackles what we call false dependencies. A programmer might reuse register names, say register A, in different independent parts of the code.
Right.
Internally, the processor actually has a much larger pool of hidden physical registers, microarchitectural registers. Our DLW2 and figure 4 to 8 could use this. The register renaming logic dynamically maps the programmer-visible architectural registers, like A, B, C, to these hidden physical registers.
Ah, so two instructions, both saying they use register A, might actually be using two different physical registers internally.
Exactly. So they don't conflict, they don't have to wait for each other unnecessarily, they can execute in parallel. The hardware sorts it out later to make sure the final results end up in the right architectural registers, it removes bottlenecks.
And structural hazards again. If you have lots of execution units, don't they all fight over accessing the registers?
That's a definite potential bottleneck. If two ALUs need to read or write simultaneously, you need hardware that can handle it. That's why registers are organized into a register file. Think of it like a small, super fast memory bank with multiple doors, multiple read and write ports.
So multiple units can access it at once.
Yes, accessing different registers within the file concurrently. And sometimes really wide processors have multiple separate register files, maybe one for integer math, one for floating point. Reduces contention, speeds up access, like having multiple tellers at a bank.
Okay, all this processing is super fast. But main memory, where the bulk of the data lives, is way slower. How do we bridge that gap?
Yeah.
That's caching, right? The memory hierarchy.
Exactly. There's a whole hierarchy of memory, as figure 5.2 shows. At the top, fastest and smallest are the registers, then caches, then main memory, RAM, then slower storage like SSDs or hard drives. Caches are key. They're smaller, faster memory layers that store copies of data and instructions that are likely to be needed soon.
Stuff you just used, or stuff nearby.
Right. The idea is to keep frequently used info closer to the processor. There are levels. L1 cache is tiny and fastest, right on the core. L2 is bigger, slightly slower. Sometimes L3, bigger and slower still. If the data the CPU needs isn't a cache hit, it's super fast. If not a cache miss, it has to go to the slower main memory. Big difference.
And putting caches right on the CPU chip helps.
Massively. Shorter distances mean faster access. On-die L1 and L2 caches are standard now.
Let's look at some real-world evolution. Intel's Pentium line. How did things change after the original Pentium?
Well, the Pentium Pro, the P6 microarchitecture, was a huge leap. Figure 5.6 shows its structure. It introduced things like the reservation station.
What did that do?
It acted like a waiting room for instructions. Decoded instructions would sit there until all their data operands were ready. This enabled out-of-order execution. Instructions didn't have to run strictly in program order if their data was ready earlier, and it wouldn't mess up the result.
Faster processing if things aren't held up unnecessarily.
Exactly. And the P6 also had a reorder buffer, the ROB. It tracked the original instruction order so results could be written back correctly even if executed out of order. This separation of fetching decoding from execution was key. Pentium II, figure 511, refined this, boosted speed. Pentium III, figure 512, added more features like SSE instructions for better multimedia and vector math. Though it's fair to say, while dominant, these Pentiums weren't always the absolute performance kings compared to some contemporary RISC designs, transistor for transistor.
Speaking of RISC, what about PowerPC? Especially the ones Apple used for so long.
Right, the PowerPC family, Apple, IBM, Motorola collaboration, interesting designs there too. The early 601 was notable for a pretty big L1 cache for its time, 32 KB unified, helped it compete with Pentium's integer performance.
Yeah.
The 603, 603E focused more on low power, good for laptops. The 604, 604E were the higher performance desktop workstation chips. Deeper pipelines, bigger caches, Table 6.3 details some of that. Then the PowerPC 750, which Apple called the G3, even with a relatively short pipeline like the 603, it had smart improvements like much better branch prediction using history tables.
Predicting those jumps better.
Yep. And the 7400, the G4, that's where Ultivec came in the vector unit. Big boost for multimedia. But a key challenge for the G4 line was that its shorter pipeline made it harder to crank up the clock speeds to match what Intel and AMD were doing in the gigahertz race.
So, different philosophies. The book contrasts Intel's Pentium 4 and Motorola's G4E specifically, narrow and deep versus wide and shallow.
Yeah, that's a great way to put it. Figure 7.3 illustrates this. The Pentium 4 around 2000 went narrow and deep. They aimed for extremely high clock speeds. The cost. A very, very long pipeline, maybe 20 stages or more in some versions.
Wow, 20 stages.
Yeah. It needed really aggressive branch prediction and big buffers to try and keep that long pipe fed. The Motorola G4E, in contrast, was wide and shallow, shorter pipeline, maybe 7 stages, but it focused on having more execution units in the back end.
So, doing more instructions in parallel.
Exactly. Trying to maximize instruction-level parallelism, ILP. Pentium 4 chased raw clock speed. G4E chased parallelism. P4 also had a huge instruction window, holding like 126 instructions for lots of out-of-order execution. G4E used things like issue queues to smooth the flow to its multiple execution units, two very different bets on how to get performance.
Then the industry moved towards 64-bit computing. How did x86 handle that with x86 64?
The shift to 64-bit, initially driven by AMD's x86-64 design, which Intel later adopted, was mainly about two things. Bigger general-purpose registers moving from 32 bits to 64 bits, like Figure 9:1 shows, and a much bigger address space.
Getting past that 4 GB RAM limit of 32-bit.
Exactly. That was becoming a real bottleneck. x86-64 blew the doors off, theoretically allowing access to huge amounts of memory, 256 terabytes virtual, initially maybe 1 terabyte physical. Figure 9:3 shows the expanded model, 64-bit registers, 64-bit PC, but the genius of x86-64 was its backward compatibility. It had different modes, as Figure 9:4 and Table 9:1 outline, legacy mode for old 32-bit OCs, compatibility mode for 32-bit apps on a 64-bit OS, and the full 64-bit mode.
So stuff still worked.
Mostly, yeah. It allowed a smoother transition while unlocking the power of 64-bit for new software. More than just memory, it changed data handling.
And on the PowerPC side for 64-bit, the PowerPC 970, based on IBM's Power 4 server chip, what was its approach?
The 970, yeah, derived from the powerful Power 4. It aimed for both width and depth, really. A very ambitious design. It could fetch and decode a whopping 8 instructions per cycle. It used an internal format called IOPs, internal operations.
8 instructions. Wow.
Yeah. Most PowerPC instructions became one IOP. Some complex ones got cracked into 2 or even millicoded into several for really complex stuff. A key part was its front-end pre-decoding and dispatch grouping. Instructions were marked on how they should be bundled together for the execution units. It could hold 4 such groups.
Sounds efficient.
Potentially very high throughput, yes,
Yeah.
but it was sensitive. If instructions couldn't be grouped well, or if a group stalled, it could bottleneck. Needed careful code optimization. The back end was powerful too. 2 integer units, dedicated units for condition registers and branches. 2 load score units, double the memory bandwidth of the G4E, and 2 FPUs.
Strong vector capabilities, too.
Yes, significant vector power, feeding multiple vector units via logical issue queues, as you see in figures 10.3 and 10.6. Overall, a very capable chip, but that group dispatch scheme had performance nuances.
Well, flipping back to caching again, the book uses a furniture workshop and lumber warehouse analogy. Can you walk us through that? It sounds helpful.
It's a great analogy. Okay, CPU is the busy workshop. Main memory is the huge lumber warehouse far away. Getting wood from the warehouse every time, slow. Inefficient.
Right.
Caching is like building a smaller lumber yard right in town. It stocks the wood types the workshop uses most often. Now, the workshop usually gets wood much faster from the local yard that's a cache hit.
Makes sense.
But if the local yard doesn't have the specific wood needed to cache miss, you still have to make the slow trip to the main warehouse.
Oh.
And the levels. L1 cache is like a tiny shelf right inside the workshop for immediate needs. L2 is the in-town lumber yard.
Okay.
Then concepts like locality, spatial locality, needing several pieces of the same wood, or wood stored together, like building a table. Temporal locality, needing the same tool or wood type repeatedly in a short time. Cache pollution is when the local yard gets cluttered with less useful wood, pushing out the good stuff.
Yep.
And how the yard is organized matters. Direct mapping, figure 11-7. Each wood type has only one specific spot. Can cause conflicts. Set associative mapping, figures 11-8, 11-9, like having multiple bins for each wood type. More flexible, fewer unnecessary trips to the warehouse.
Like four-way set associative, 4 bins per type.
Exactly. Replacement policies decide which wood gets kicked out when new wood arrives. Block size is how much wood you move at once between warehouse and yard. All these affect cache performance.
We've covered so much. Let's just briefly touch on Intel after Pentium 4. Pentium M, Core Duo Solo. What were the big steps there?
Right. Pentium M and then Core Duo Solo marked a major shift for Intel. Moving away from the netburst architecture of the P4, that long pipeline, high-power draw, the focus shifted dramatically towards energy efficiency and getting more performance per clock cycle.
Smarter, not just faster clocks.
Exactly. Pentium M introduced micro-ops fusion, shown in figure 12-5. Certain common by 86 instructions that usually broke into 2 internal micro-ops could now be fused into 1. Made decoding more efficient, especially for memory stuff. Core Duo Solo built on that. They extended micro-ops fusion to SSE instructions, which was a weak spot in Pentium M. And they added macro fusion, fusing 2 entire by 86 instructions into 1 micro-op before decoding. Boosted the front-end throughput.
Okay, more efficiency tricks.
Yep. The core architecture also widened the execution engine, handled full 128-bit SSE instructions better, table 12-4, figure 12-15, improving floating point and vector speed significantly. They also added clever things like memory disambiguation, figures 12-17 to 12-19, to avoid unnecessary stalls caused by potential memory access conflicts. Ultimately, Core, especially with the dual-core Core 2 duo, figure 12-9, really cemented Intel's move to multi-core designs. They realized just cranking clock speed wasn't the future anymore.
Wow, okay, that really has been a deep dive, an
Yeah.
incredible journey inside the machine. So to boil it down for everyone listening, what are the absolute must-remember takeaways?
Well, first, that fundamental read-modify-write cycle is what computers do. Second, how instruction execution evolved.
Yeah.
From simple sequential steps to pipelining's overlapping stages, and then superscalars parallel execution. Big leaps in speed.
Right.
Third, the ISA, the instruction set architecture, is that vital link between software and hardware and how it grew over time. Fourth, the memory hierarchy and caching are absolutely critical for performance, bridging that speed gap between CPU and RAM.
Can't forget caching.
Definitely not.
Yeah.
And finally, seeing the different design philosophies, Intel chasing clock speed, then shifting, PowerPC focusing on parallelism, and the eventual industry move towards multi-core and efficiency.
It's amazing how those core ideas still drive everything today. It really makes you consider the balancing act involved in designing modern chips, doesn't it?
It really does. I mean, think about those trade-offs we discussed. Clock speed versus parallelism. How big and smart can caches get? Do we need more specialized instructions for AI or graphics? These questions are still central to designing today's multi-core processors, specialized accelerators. It makes you wonder, what are the next clever tricks architects will come up with to push performance further? It's a fascinating ongoing story.
It certainly is a great thought to end on. And if this deep dive sparked your interest, definitely check out the source, Inside the Machine by John Stokes. It's a fantastic read for going even deeper. Thanks for joining us for this deep dive.